For eons, humanity has gazed upon the night sky, pondering its mysteries. What is this vast expanse, teeming with stars and galaxies? Is it merely a cold, inert void, governed by predictable laws? Or is there something more profound, a vibrant essence that binds everything together? We are about to embark on a journey, exploring the universe not as a static backdrop, but as an intricately woven tapestry of dynamic processes, constantly evolving, creating, and even, in a profound sense, breathing. Our story begins at the very dawn of existence, an event so cataclysmic, yet so precise that it defies easy comprehension. The Big Bang, from an unimaginably hot and dense singularity. Space, time, and all matter burst into being. This wasn't an explosion in space, but rather an expansion of space itself, laying the foundational framework for everything we know. It was the universe's first breath, initiating an unstoppable cosmic evolution. In the immediate aftermath of the Big Bang, the universe was an intensely hot, opaque plasma, too dense for light to travel freely. Quarks and leptons, the fundamental building blocks of matter, swirled wildly. As the universe expanded and cooled, these particles began to combine. This era was chaotic, a cosmic soup of raw energy, dictating the very first interactions and setting the stage for more complex formations. Within fractions of a second, the universe underwent an astonishing period of exponential growth known as cosmic inflation. This brief, rapid expansion smoothed out irregularities and stretched quantum fluctuations into the vast seeds that would eventually become galaxies and galaxy clusters. It's a concept that helps explain the remarkable uniformity we observe across the cosmos today. Approximately 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with atomic nuclei, primarily hydrogen and helium. This pivotal moment, known as recombination, made the universe transparent. Light, finally freed from the dense plasma, streamed across the cosmos, and we observe this ancient glow today as the cosmic microwave background radiation. The cosmic microwave background isn't perfectly uniform. It contains tiny temperature fluctuations, minute differences in density. These tiny ripples, amplified by gravity over billions of years, were the cosmic blueprints for all large-scale structures we see today. They whisper tales of the universe's earliest moments, telling us how the universe began to truly organize itself. Gravitational forces, subtle at first, began to pull together these slightly denser regions of primordial gas. Over millions of years, vast clouds of hydrogen and helium collapsed under their own weight. These accumulating masses were the embryonic forms of galaxies, the first truly immense structures in the universe, marking the end of the cosmic dark ages. Inside these collapsing gas clouds, immense pillars of gas and dust began to form. As more material was drawn in, their cores became hotter and denser. This process, driven solely by gravity, eventually reached a critical point where unimaginable pressures were generated, giving birth to the first stars. These were monumental in size, many times larger than our Sun. When the core of a protostar reached about 10 million degrees Celsius, nuclear fusion ignited. Hydrogen nuclei fused to form helium, releasing an enormous amount of energy. This ignition marked the birth of a true star, a self-sustaining powerhouse bathing its surroundings in light and heat. These first-generation stars were the universe's original light bulbs. These first stars were incredibly massive and burned through their nuclear fuel at astonishing rates, living fast and dying young. Their lives were brief, lasting only a few million years compared to our Sun's billions. But their demise was spectacular. Violent supernovae explosions that scattered newly forged heavier elements back into the cosmos. The death of these colossal first-generation stars was crucial for the universe's ongoing evolution. Supernovae dispersed elements like carbon, oxygen, iron, and silicon, elements heavier than hydrogen and helium that were forged in the stars, fiery hearts. These elements, essential for planets and life, were now dispersed as cosmic dust, awaiting their next role. Over billions of years, countless generations of stars were born, lived, and died. Each cycle enriched the interstellar medium with more heavy elements. This gradual cosmic alchemy transformed the pristine, simple universe of hydrogen and helium into the chemically diverse cosmos we observe today, capable of forming rocky planets and the building blocks of life. Stars often form in clusters, born from the same vast cloud of gas and dust. Our Sun is a second or third generation star, meaning it contains elements forged in previous stellar explosions. This interconnectedness highlights how everything in the universe is fundamentally recycled, each generation building upon the remnants of the last. The magnificent spiral and elliptical galaxies we observe are not static entities. They are colossal, dynamic systems, constantly engaged in a gravitational ballet. Stars orbit, gas clouds collide, and entire galaxies interact, sometimes even merging, driven by the relentless tug of gravity. This galactic dance shapes their evolution over cosmic timescales. At the heart of most large galaxies, including our own Milky Way, lies a supermassive black hole. These enigmatic objects, millions to billions of times the mass of our Sun, exert immense gravitational influence. While they consume matter, they also play a vital role in regulating star formation in their host galaxies, a complex cosmic feedback loop. Dark matter, an invisible and mysterious substance, makes up about 27% of the universe's mass. We cannot see it or directly interact with it, but its gravitational effects are undeniable. It acts as the scaffolding upon which galaxies and galaxy clusters are built, holding them together and influencing their distribution across the cosmos. Its invisible hand guides much of the universe's structure. Even more enigmatic is dark energy, which constitutes about 68% of the universe's total energy density. Unlike gravity, it acts as a repulsive force, accelerating the expansion of the universe. This discovery revolutionized our understanding of the cosmos, hinting that the universe's breathing might involve an ever-increasing outward inhale. The interplay between gravity, dark matter, and dark energy dictates the fate of the universe on the grandest scales. Will it expand forever, eventually growing cold and dark? Will it eventually recollapse in a big crunch? Or will it tear itself apart in a big rip? The universe is actively deciding its own future, influenced by these fundamental forces. These fundamental forces are not merely abstract concepts, they are the active agents that sculpt the cosmos. Gravity pulls. Strong and weak nuclear forces bind. Electromagnetism interacts, and dark energy pushes. Together, they create a dynamic, evolving system, far from a static, predetermined machine. The universe is a grand orchestra, these forces its conducting hands. The universe's initial structure, the distribution of matter and energy, was remarkably uniform, yet contained just enough tiny variations to allow complexity to emerge. This delicate balance, a Goldilocks condition, seems almost orchestrated, allowing for the formation of stars, galaxies, and eventually, the very conditions necessary for life itself. Planets are the next act in this cosmic drama, forming within the swirling disks of gas and dust that surround young stars. As gravity pulls particles together, they clump into planetesimals, then protoplanets, gradually sweeping up more material to grow into the diverse worlds we now observe throughout the galaxy. This is a complex dance of accretion. Terrestrial planets, like Earth, are born in the inner regions of these disks, where temperatures are high enough for rocky and metallic materials to condense. Giant exoplanets, on the other hand, often form further out, accumulating vast amounts of gas and ice. Each star system is a unique laboratory of planetary creation, each world a distinct experiment. Our own solar system is a remarkable example of this planetary genesis. From a collapsing nebula, our Sun formed first, and then within its dusty disk, the planets coalesced over tens of millions of years. This process wasn't instantaneous. It was a long, violent period of collisions and gravitational sorting, shaping the system we call home. Early Earth was a molten, hellish world, constantly bombarded by asteroids and comets. As it cooled, heavier elements like iron sank to form the core, while lighter silicates rose to create the mantle and crust. This process of differentiation was fundamental to creating Earth's layered structure, which influences everything from volcanism to the magnetic field. The formation of the Moon, likely from a colossal impact between early Earth and a Mars-sized object, was another pivotal event. This impact not only reshaped our planet, but also stabilized Earth's axial tilt, leading to more moderate and stable seasons, a crucial factor for the long-term development of complex life. Over vast spans of time, water, likely delivered by comets and icy asteroids, accumulated on Earth's surface, forming the oceans. The outgassing from volcanoes also contributed to an early atmosphere. These were essential steps, transforming a barren rock into a dynamic world with the potential for liquid water, a key ingredient for life. The emergence of life on Earth, known as abiogenesis, remains one of science's grandest puzzles. From non-living matter, simple organic molecules formed, then complex polymers, eventually self-replicating structures resembling primitive cells. This transition, from chemistry to biology, implies the universe has mechanisms to foster increasing complexity. The earliest forms of life were single-celled organisms, archaea and bacteria, thriving in extreme environments. They lived for billions of years, slowly transforming Earth's atmosphere and oceans. Their simple existence laid the groundwork for all subsequent evolutionary developments, demonstrating life's incredible resilience. A monumental leap occurred with the evolution of photosynthesis, allowing organisms to harness the sun's energy and release oxygen. This great oxidation event fundamentally reshaped Earth's atmosphere, leading to the formation of the ozone layer and paving the way for more complex oxygen-breathing life forms. The rise of multicellular life was a revolutionary advance, allowing for specialization and greater complexity. From simple colonies, organisms evolved with distinct tissues, organs, and ultimately sophisticated body plans. This innovation unleashed an explosion of biological diversity, filling every available ecological niche. Over hundreds of millions of years, life on Earth diversified and evolved through natural selection, adapting to changing environments and filling new ecological roles. From the oceans, life ventured onto land, conquering new frontiers and giving rise to an astonishing array of flora and fauna. Evolution is the universe's grand experiment in adaptation. Mass extinction events, though devastating, have been a recurring feature in Earth's history. These cataclysms, triggered by asteroids, volcanism, or climate shifts, wipe out vast numbers of species. Yet, life always recovers, evolving new forms and filling the vacated niches, demonstrating its enduring resilience and adaptability. The incredible biodiversity we see today, from microscopic bacteria to towering redwoods and complex mammals, is the cumulative result of 4 billion years of continuous, dynamic evolution. Each species is a testament to life's capacity to adapt, diversify, and thrive across a myriad of environmental conditions. Humanity, too, is a product of this cosmic and biological evolution. Our intelligence, curiosity, and ability to comprehend the universe are remarkable outcomes of billions of years of development. We are the universe's way of looking back at itself, an emergent property of its intricate processes. The elements that compose our bodies, carbon, oxygen, nitrogen, iron, were forged in the hearts of distant, ancient stars and scattered across the cosmos by supernova. We are, quite literally, stardust. This profound connection unites us with every star, every planet, every nebula in the universe. The universe is not merely home to life. In a profound sense, it is alive. It is born, it grows, it evolves. It forms structures, interacts, and recycles its components. It fosters self-organization, from galaxies to living cells. This dynamic aliveness is etched into the very fabric of space-time. Consider the cosmic recycling of matter. Stars create heavy elements, then die, dispersing them into space. These elements then form new stars, new planets, and eventually, life. This continuous cycle, from birth to death and rebirth, mirrors biological processes on Earth, but on a grander cosmic scale. Galaxies are like cosmic ecosystems. They are born, grow, merge, and die. They have internal dynamics, interactions, and feedback loops that regulate their activity, much like a complex organism. They are not static collections of stars, but vibrant, evolving communities. Even on a geological scale, planets like Earth exhibit lifelike qualities. Plate tectonics constantly reshapes continents. Volcanism recycles crustal material, and atmospheric processes regulate climate. These are dynamic internal processes, interacting with external factors like solar radiation, creating a complex, responsive system. The vast network of galaxies, interconnected by the cosmic web, resembles the neural pathways of a colossal brain. Each galaxy is a node, exchanging matter and energy, influencing its neighbors across immense distances. This grand structure suggests an interconnectedness that transcends individual components. Our Sun, a rather ordinary star, has been remarkably stable for billions of years, providing the consistent energy needed for life to thrive on Earth. Its steady output, governed by precise physical laws, is itself a testament to the universe's capacity for sustained processes over immense timescales. The Earth's magnetic field, generated by the convective motion of molten iron in its outer core, acts as a protective shield. It deflects harmful solar wind particles and cosmic rays, creating a habitable zone on our planet's surface. Without this dynamic shield, life as we know it might never have survived. The seasons on Earth, crucial for many biological cycles, are a direct result of our planet's axial tilt as it orbits the Sun. This subtle tilt, a consequence of Earth's formation and the Moon's influence, provides the varied climates that drive biodiversity and ecological activity. The water cycle, evaporation, condensation, precipitation, is a perpetual motion machine, continuously cleansing and distributing this vital liquid across the planet. This cycle shapes landscapes, sustains ecosystems, and ensures the continuous availability of fresh water for life. It's Earth's internal circulation system. The carbon cycle, involving the exchange of carbon between the atmosphere, oceans, land, and living organisms, is another fundamental process. It regulates Earth's climate and provides the building blocks for all organic matter, demonstrating the planet's vast metabolic activities. Over deep time, the atmosphere of Earth has undergone dramatic transformations, largely driven by life itself. From a primordial mix dominated by carbon dioxide and nitrogen, it became oxygen-rich due to photosynthetic organisms, fundamentally altering the planet's chemistry and habitability. Plate tectonics, the movement of Earth's rigid outer shell, creates vast mountain ranges, deep ocean trenches, and volcanic activity. This slow, continuous geological breathing recycles crustal material, influences climate, and maintains the Earth's internal heat, driving long-term geological cycles. Intricate interconnectedness of ecosystems on Earth mirrors the universal interconnectedness. Every species, every natural process is linked in a vast, sensitive web. Disrupt one part, and the effects ripple throughout the entire system, much like an interconnected cosmic body. The origin of species is not a linear march towards complexity, but a branching, improvisational dance of adaptation and diversification. Evolution explores countless possibilities, shaping life to fit every conceivable niche. This ongoing process reflects the universe's boundless creative potential. From the tiniest bacteria to the largest whales, life on Earth exhibits an incredible drive to persist, reproduce, and adapt. This inherent vitality, evident at every scale, is perhaps the ultimate expression of the universe's active, self-sustaining nature. Life is the universe seeking to understand itself. Beyond Earth, the search for extraterrestrial life is a profound quest. If life emerged independently elsewhere, it would imply that the principles supporting it are common throughout the cosmos, strengthening the notion that life is a natural, perhaps inevitable outcome of cosmic evolution. The conditions necessary for life, often referred to as Goldilocks zones, are not merely about liquid water. They include a star of the right size and lifespan, a stable orbit, a protective atmosphere, and the presence of heavy elements. These complex requirements highlight the universe's refined tuning. Exoplanet discoveries are revealing a staggering diversity of worlds: super-Earths, mini-Neptunes, hot Jupiters. Each new discovery expands our understanding of planetary systems and the potential for life to adapt to vastly different cosmic environments, perhaps very different than Earth. The concept of panspermia suggests that life, or its building blocks, might travel between planets, perhaps hitchhiking on meteorites. This intriguing idea implies that life's journey isn't confined to a single world, but might be a cosmic phenomenon, spreading its seeds across star systems. Even if life is rare, the sheer immensity of the universe and the countless stars and planets within it mean that the probability of life existing elsewhere remains high. The universe is a vast cosmic laboratory, continuously running experiments across billions of star systems. The universe's constant expansion means that much of it is now forever beyond our observable reach, as galaxies recede faster than light can travel. This accelerating expansion paints a picture of a dynamic universe, where the boundaries of what we can perceive are ever-shifting. Neutron stars, the ultra-dense remnants of massive stars, spin incredibly fast and possess magnetic fields trillions of times stronger than Earth's. They are cosmic dynamos, radiating immense energy and acting as unique laboratories for extreme physics, even creating heavier elements like gold through their mergers. Black holes, not just supermassive ones at galactic centers, but also stellar mass black holes, play crucial roles in their stellar neighborhoods. They are cosmic vacuum cleaners, recycling matter and energy back into the universe, shaping the evolution of stars and nebulae around them. The cosmic dance of galaxies often leads to collisions. While individual stars rarely collide, the gravitational interactions reshape entire galaxies over millions of years, triggering bursts of star formation as gas clouds compress. These galactic mergers are acts of cosmic creation and destruction. Quasars, incredibly luminous, active galactic nuclei, are powered by supermassive black holes accreting vast amounts of matter. They were much more common in the early universe, acting as cosmic lighthouses, their brilliant glow illuminating the distant past and revealing how galaxies grew. The universe's fundamental constants, like the strength of gravity or the mass of an electron, appear to be finely tuned to allow for the existence of complex structures, stars, and life. Even slight deviations would render the universe a far simpler or lifeless place, begging questions about its deeper nature. Cosmic rays, high-energy particles originating from supernovae and other extreme cosmic events, constantly bombard Earth. While often seen as a hazard, they also play a role in atmospheric processes and perhaps even influenced early life's mutations, an invisible connection to the universe's most violent phenomena. The interstellar medium, the vast emptiness between stars, is not truly empty. It's a dynamic mix of gas, dust, cosmic rays, and magnetic fields. This seemingly inert space is actually the raw material for future stars and planets, constantly being enriched and churned by stellar processes. Galactic rotation is a mesmerizing display of organized motion. Stars, gas, and dark matter orbit the galactic center, creating the iconic spiral arms. This rotation is not uniform. Different parts move at different speeds, creating dynamic waves that trigger new star formation. The universe is not just expanding, but doing so at an accelerating rate. This startling discovery, attributed to dark energy, profoundly impacts our future. It means far-off galaxies will eventually recede beyond our cosmic horizon, making the universe appear emptier and lonelier in epochs to come. Gravitational lensing, where massive objects like galaxy clusters bend and magnify the light from more distant galaxies, acts as a natural telescope. It allows us to peer back further in time, observing some of the earliest galaxies and understanding the distribution of dark matter throughout the cosmos. The universe is permeated by a cosmic neutrino background, a relic radiation from the Big Bang, similar to the cosmic microwave background but composed of elusive neutrinos. These nearly massless particles zip through everything, a ghostly cosmic messenger carrying information from the very early universe. The search for gravitational waves, ripples in spacetime caused by cataclysmic cosmic events like black hole mergers, has opened a new window onto the universe. We can now listen to the universe's most violent phenomena, gaining insights previously unattainable, hearing its deep cosmic rumblings. The vast emptiness of space is often portrayed as cold and silent, yet it hums with energy, from distant pulsars sending out rhythmic beats to the faint echo of the Big Bang. The universe is a symphony of subtle radiations and cosmic background noise, a constant murmur of activity. Gamma-ray bursts, the most powerful explosions in the universe, are often associated with the collapse of massive stars into black holes or the merger of neutron stars. These transient but incredibly energetic events are like cosmic fireworks, signaling extreme physical processes far across the cosmos. The sun's activity, including solar flares and coronal mass ejections, directly impacts Earth's magnetosphere and atmosphere, causing phenomena like auroras and potentially affecting technology. This direct connection reminds us that our planet is part of a larger, active solar ecosystem. Asteroids and comets, the leftover debris from the formation of our solar system, are not just potential hazards. They are time capsules, preserving primordial material and potentially delivering water and organic molecules to early planets, playing a vital role in planetary evolution. The Kuiper Belt and Oort cloud, immense reservoirs of icy bodies beyond Neptune, are home to countless comets. These distant, cold regions represent the outer limits of our sun's gravitational influence. A vast, dormant frontier awaiting disruption to send icy visitors towards the inner solar system. The presence of liquid water, whether on Earth's surface or beneath the icy crusts of moons like Europa and Enceladus, is a primary indicator of potential habitability. These subsurface oceans, warmed by tidal forces, offer intriguing possibilities for life beyond our planet. The complex ecosystems found around deep-sea hydrothermal vents on Earth, thriving without sunlight, demonstrate life's adaptability to extreme conditions. This opens tantalizing possibilities for similar life forms in the subsurface oceans of icy moons, powered by chemosynthesis. The concept of a multitude of universes, or a multiverse, suggests that our universe might be just one bubble in an infinitely larger cosmic foam. While speculative, it implies a boundless cosmic creativity, where every possible physical law and condition might exist across an infinite expanse. Astronomical observations continually refine our understanding of the universe's past, present, and future. Through powerful telescopes and sophisticated data analysis, we are piecing together the universe's autobiography, chapter by countless chapter, revealing its deepest secrets. Dark matter and dark energy are not merely placeholders for unknowns. They represent fundamental components of the universe that hint at physics beyond our current understanding. Their existence challenges us to expand our models and confront the truly unknown dimensions of reality. The universe's accelerating expansion will eventually scatter galaxies so far apart that future civilizations will see only their own galaxy in the night sky. This cosmic isolation, a product of dark energy, implies a future where our current understanding of a vast cosmos may be forgotten. The eventual fate of our sun, growing into a red giant and potentially engulfing Earth, then shrinking into a white dwarf, is a natural conclusion to stellar life cycles. This stellar transformation is an inevitable part of the universe's continuous processes of birth, change, and eventual rest. After the white dwarf stage, our sun will slowly cool over trillions of years, eventually becoming a black dwarf, a theoretical, cold, dark remnant. This distant cosmic destiny highlights the immense timescales over which cosmic processes unfold, far beyond human comprehension. Even after all stars have exhausted their fuel, the universe will still be dynamic. Black holes will slowly evaporate through Hawking radiation, and matter will gradually decay into fundamental particles. This ultimate heat death is a cold, slow dissolution, a final, drawn-out exhalation. The universe's grand scale, its billions of galaxies, each with billions of stars, compels humility. We are but a tiny speck in a cosmic ocean, yet our ability to observe, measure, and understand this immensity is perhaps its greatest marvel. Our existence is a brief, conscious flicker in cosmic time. The cosmic dance of creation and destruction is ceaseless. Supernovae scatter elements, which form new stars. Galaxies collide, leading to fresh bursts of star formation. Even black holes, once thought to be only destroyers, can influence star formation, showing continuous feedback loops. The precise laws of physics that govern the universe, from gravity to quantum mechanics, are remarkably consistent across vast distances and timescales. This underlying order allows for predictability and the emergence of complexity, making the universe comprehensible to us. The concept of cosmic consciousness suggests that the universe itself might possess a form of awareness distributed across its vast network of interactions. While highly speculative, it's a thought-provoking idea that challenges our anthropocentric views of intelligence and life. Humanity's drive to explore space, to send probes to distant planets, and to search for signs of alien intelligence is an intrinsic part of the universe's dynamic. We are its conscious agents, extending its reach and seeking to understand its deeper secrets. The light we receive from distant galaxies left them billions of years ago. When we look up at the night sky, we are looking back in time, witnessing the universe as it once was. This makes cosmology a form of cosmic archaeology, digging through layers of time. The formation of the first stars, known as population 3 stars, was a pivotal moment. Composed solely of hydrogen and helium, they were the universe's pristine original builders. Though never directly observed, their existence is inferred and critical to cosmic history. The concept of the habitable zone around a star is dynamic. It shifts over time as a star evolves, impacting the long-term potential for life on orbiting planets. A planet that is habitable now may not be in the distant future. The incredible complexity of life, from the intricate machinery within a single cell to the vast neural networks of a brain, emerged from simpler components through billions of years of evolution. This self-organization is a hallmark of the universe's creative power. Rogue planets, those not gravitationally bound to any star, wander aimlessly through interstellar space. Once thought rare, they may be a common feature of the galaxy, hinting at processes that eject planets from their stellar nurseries. The composition of the universe, with its disproportionate amounts of dark matter and dark energy, indicates that we understand only a fraction of its total content. The visible universe, with all its stars and galaxies, is merely the tip of the cosmic iceberg. Cosmic filaments, immense strands of galaxies and dark matter, span hundreds of millions of light-years, connecting galaxy clusters. This vast structure suggests a universe that is far from randomly distributed, rather ordered into a grand, beautiful network. The universe's expansion isn't uniform at all scales. On galactic and cluster scales, gravity still dominates, binding systems together. It's only on the largest scales that dark energy's expansive force truly takes over, creating a layered dynamic. The energy from distant supernovae can also influence planetary atmospheres. These powerful blasts release high-energy particles that can strip away planetary atmospheres over cosmic timescales, affecting their long-term habitability. Pulsars, rapidly rotating neutron stars, emit beams of electromagnetic radiation that sweep across space like cosmic lighthouses. Their incredibly precise timing makes them invaluable for astronomers, acting as cosmic clocks and probes of space-time. The universe is not a static painting. It's a dynamic sculpture, continuously carved and reshaped by forces we are only beginning to comprehend. Every moment, stars are born and die, galaxies merge, and space itself expands, a constant cosmic metamorphosis. The concept of exoplanet atmospheres offers a new frontier in the search for life. Spectroscopic analysis can detect elements like oxygen, methane, or unique biosignatures, potentially revealing if alien life has fundamentally altered its planetary environment, just as ours has. The universe's fine-tuning, the precise values of its fundamental constants, is a source of profound philosophical wonder. Is it a mere cosmic fluke, or does it hint at a deeper organizing principle, an underlying intelligence, or a natural propensity for complexity? The phenomenon of galactic cannibalism, where larger galaxies absorb smaller ones, is a critical part of galactic evolution. Our Milky Way is currently eating several smaller dwarf galaxies and is on a collision course with the Andromeda Galaxy. Stellar nurseries, cold, dense clouds of gas and dust like the Orion Nebula, are breathtaking sites of continuous star formation. Inside these cosmic wombs, gravity relentlessly pulls matter together, endlessly birthing new generations of stars. The chemical enrichment of the universe is a slow, methodical process over billions of years. Each stellar generation contributes more heavy elements, making subsequent star and planet formation increasingly diverse and complex. The universe's expansion not only separates galaxies, but also cools the residual heat from the Big Bang. As space stretches, the wavelengths of photons stretch with it, gradually reducing the overall temperature of the cosmos towards absolute zero. The intricate details of planetary formation, from the accretion of dust grains to the eventual clearing of orbital paths, demonstrate a complex interplay of gravitational forces, collisions, and angular momentum, leading to stable, long-lived systems. The possibility of cosmic terraforming, altering a planet's environment to make it habitable, is a dream of future humanity. It exemplifies our growing capability to interact with and potentially reshape cosmic processes, mirroring the universe's own creative power. The ongoing discovery of new atmospheric phenomena on other planets, like methane rain on Titan or vast dust storms on Mars, reveals the unique and active meteorological processes shaping each world, driven by its individual conditions and energy sources. The cyclical nature of life on Earth, from the daily ebb and flow of tides influenced by the moon, to the seasonal changes driven by the sun, highlights our planet's deep connection to its celestial neighbors. We are part of a cosmic clockwork. The universe is still actively forming large-scale structures. Galaxy clusters are continuing to grow, pulling in more galaxies and dark matter, demonstrating that cosmic evolution is far from complete, a continuous construction project. Even seemingly empty voids in the cosmic web, vast regions with very few galaxies, are not truly devoid of matter. They contain thinly spread dark matter and early hydrogen, remnants of the universe's initial homogeneity, slowly flowing towards denser regions. The future of space exploration promises to reveal ever more about the universe's aliveness. Missions searching for biosignatures, deep space telescopes peering back to the first stars, and gravitational wave observatories will continue to unravel its dynamic story. The universe rewards patience. Events like stellar evolution, galactic mergers, and the emergence of life unfold over unimaginable timescales, requiring billions of years. Understanding the cosmos demands a shift in perspective beyond human lifespans. The concept of a living cosmos is not merely poetic. It's rooted in the continuous energy flow, transformations, and self-organizing properties observed at every level, from subatomic particles to the largest cosmic structures. From the quantum foam of empty space, virtual particles flicker in and out of existence, a constant energetic hum at the very smallest scales. Even the nothingness of the vacuum is teeming with dynamic potential, contributing to the universe's overall aliveness. The universe acts as a colossal calorimeter, slowly dissipating its initial energy. Its overall temperature is dropping, and its entropy is increasing. Yet, within this inexorable trend, localized pockets of decreasing entropy, like life, thrive and grow. The dance between expansion and gravity is what gives the universe its structure. Expansion drives galaxies apart, but gravity pulls them together into clusters and filaments, balancing vastness with intricate organization. The light of distant quasars and the cosmic microwave background provide direct evidence of the universe's dynamic evolution. These cosmic fossils tell a cohesive story of a universe that has never been static, always changing, always alive. The universe is not just creating new stars. It's also constantly reforming its chemical composition. Heavy elements from supernova explosions mix and enrich the interstellar gas, setting the stage for even more complex chemistry and potential life in future generations. Our own individual lives, brief as they may be, are intimately connected to the life of the universe. We are made of its elements, powered by its stars, and our very consciousness is an emergent property of its grand, evolving processes. As we continue to unravel the universe's secrets, the line between living and non-living becomes increasingly blurred. The cosmos, with its ceaseless activity, interconnectedness, and propensity for self-organization, truly embodies the essence of being alive. Beyond the stars, beyond the galaxies, there are still profound mysteries. The nature of consciousness, the possibility of other fundamental forces, or the very beginning of the Big Bang itself remain fertile grounds for future discovery, hinting at deeper layers of cosmic aliveness. The universe's constant striving for equilibrium, yet its simultaneous capacity for continuous instability and change, is a fascinating paradox. It's a system that balances order with chaos, predictability with emergent wonder, ensuring its perpetual animation. Even the smallest particles, the quanta of energy and matter, are in constant motion, vibrating, interacting, transforming. The universe is awake and active at its most fundamental levels, a truth that underscores its vibrant and ever-present dynamism. We are not just observers of this grand cosmic play, but active participants. Our understanding, our curiosity, and our very existence contribute to the self-awareness of the universe, a magnificent cycle where the cosmos reflects upon itself through conscious beings. The universe is not a machine, but a grand, evolving organism. It is born, it breathes, it creates, it explores, and it dreams. The universe is truly alive, and in that profound realization, we find our deepest connection to everything around us.